So we could take this complementary pair set of transistors where we've got an NPN and a PNP, just tack that on the back of, say, a non-inverting amplifier. What we're getting now is essentially a current boosting. See, we have up to 25 milliamps here, and that's going to become, if it's positive, the base current of Q1, and then I can get beta DC, or even the beta AC, times that base current. Likewise, when current comes in here, we can sink 25 milliamps here, again, neglecting what's going to go down here. We can get effectively the DC beta times the 25 milliamps that we have here. If you had a beta on the order of 50, we're looking at 625 milliamps of current now available for the load. And so that would be easily driven 4 ohm or an 8 ohm load. The problem with this circuit is that we have that crossover distortion as our transistors being turned on and turned off. That crossover distortion would be very audible, and so if we had something at 1 kilohertz, we could hear that turning on and turning off of the transistors. So what we can do is use the idea of feedback and kind of go back to a derivation that we did in ECE 201, and that is taking a look at the output voltage versus the input voltage of, say, a non-inverting amplifier when we consider the fact that the op-amp is a voltage-controlled voltage source. Just repeating the derivation that's in the ECE 201 notes. But let me go over it again too here. The voltage that's across the op-amp input terminals is amplified by some gain factor. I'll call that A sub dm. It stands for differential mode gain. We'll talk more about this if you take the course ECE 402. And so that's what's between this node and ground. So I've got my resistors R2 and R1. And there's a voltage across R1. Because there's no current here, the current in R2 is the same as R1. So I've got a voltage divider with the controlled source, which is equal to V out, with the resistor R1 over R1 plus R2. So I'll call that voltage V sub Y. The voltage V sub S is equal to this drop plus this drop, which is V sub X plus V sub Y. Now the output voltage is equal to ADM times V sub X, and so I could solve then for V sub X as V out over ADM, and then V sub Y is equal to V out times this voltage divider. So I could pull out the V out and be left with these two terms, and then I could divide by V sub S and then take the reciprocal of this. Now let me pull out a term here. Let me pull out this R1 over R1 plus R2, and then putting it in the numerator I get the reciprocal. Pulling that term out, because there was none here, I've got to basically put the reciprocal of it there, and then of course I got just one left over. So if you take the limit as ADM goes to infinity, this term drops out and we get a gain of 1 plus R2 over R1, which is our classical definition of a non-inverting amplifier with infinite gain. This term in yellow is called the error factor. What it represents is that if ADM is not infinite, this represents an error to what you would expect if you had an infinite gain op-amp. But what's interesting is this term just needs to be large. If it's large, of course we're just back to this ratio, but if it's large and nonlinear, that's also still true. Adding this circuit, we're really getting a gain of 1 for voltage, although it's a little bit of a nonlinear gain. It's going to be added to, or really multiplied by, the open loop gain of the op-amp. So if we put feedback around this, we'll get still a non-inverting amplifier, but now the ability to get a lot more current out because 25 milliamps here can get amplified by the DC beta of the transistor. We're going to take a look at lab and moving the wire from here to see the reduction in crossover distortion. Now we only got one speaker on the bench, and so I'm going to take your MP3 player or CD player, or even if you have a tape player, this will work too, and I want to add the two channels together. So we could use one of the circuits we did in ECE 201 or 202 or 203, which is the inverting summer. If I take two equal resistors here, the signal here is the ratio of the resistor times the input. So this would give me a gain of about 100 for the left channel and then for the right channel, and what I get is the summation of those two. Now sometimes coming off of the output of an MP3 player, we might get some DC levels. And so I want to block the DC if I can, mostly because this will eventually go to the speaker through the power amplifier. Let's block any DC that's coming in here. I picked a value of R and C such that I would pass the audio bandwidth frequencies. Now let's do a calculation on this. This pod is going to be hooked up to the non-inverting power boosting amplifier that we have right here, and we're not drawing any current coming in here because the current going into the op-amp is very, very small. Effectively, whatever voltage I have here, I can voltage divide it down with just a potentiometer. The voltage here, I'll call it V audio, is a voltage divider with the output of this summing circuit times the resistor here of 50K, voltage divided with the capacitor of 0.01 microfarad. So the audio signal is what's coming out of the summer times 50K over 50K plus 1 over j omega c. You multiply through by j omega c. Got that times 50K, and then just a 1, and then in the numerator the same thing of j omega c times 50K. If you multiply this out and write it as 1 over, it actually turns out to be 200, and likewise over here. If you pull out a factor of 2 pi, that's around 32 hertz. What this means is that when the frequency of omega, which is 2 pi f, is greater than 200, which corresponds to 32 hertz, this term is much, much larger than this term, because that would give me a number here greater than 1. For frequencies above 32 hertz, we're going to pass the entire signal, but we're going to block DC. So we're going to get a gain of 100 out of this circuit. The reason I'm putting this here is that we're going to eventually feed some more signals in here. I need a lot of gain for an AM receiver that we're going to make in just a few more pages. Then we have a voltage divider with a pot, and you could think of the pot as having a percentage of the total resistance. Say the bottom half is alpha times the pot value, and the top part of it is 1 minus alpha. We've done this before in previous labs. And so the voltage divider then would be the lower half over the lower half plus the upper half. But because we've got alpha times 50K and minus alpha times 50K, the denominator just becomes just equal to 1 times the 50K, and then the 50Ks cancel, and so it's independent of the value of the pot. And then the signal that we're feeding to the power amplifier is just a percentage of the signal that's coming in. So we've got some ability to do a volume control. Again, the reason we want to block the DC here is that any DC coming in would see a gain of 100, and then potentially a gain of 11 through the next stage. And this would just simply push the cone of our speaker in one direction or the other, depending on the sign of it. Originally, when I built this circuit, I didn't put the blocking capacitor in, and it sounded horrible. And I noticed that the cone was actually pushed to one extreme end, and had to remember that I really need to put a blocking capacitor in. So even though I've learned this and I've done this for many, many years, when I was doing this initially, I didn't really think about that. But this is part of building stuff and seeing what it does.